jotting down notes in this nice little notebook instead of doing what I should have been doing. So, without further ado, let's get into it then. And I am streaming to YouTube, so this is live. So if you're watching it later, I've not edited this or anything, so it's in there warts and all. But there's some good things about that because it means maybe you'll get some commentary that you wouldn't otherwise get if it were an edited and scripted down video. Okay, so overview of the topic then. So what is logic? Well, logic is, oh no, my pen isn't working. Oh, I turned it off, that's why. There we go. Nearly a disaster already. So logic is a kind of like, it's looking at inference basically. So how do we make inferences? And when we infer from one thing, which would be like our premises, to some other thing, which would be some conclusion or something that we want to establish. And the study of logic is the study of valid inference, right? That's what it is in its most general form. Now, we make inferences all the time, and the way that we articulate these inferences comes to us pretty naturally in natural language. You might say, well, why did you go to the shops? And you might answer, because I wanted to satisfy some desire or something like that. So you might say, well, where did I put my keys? And someone will say, to the left of the bookshelf, and you'll be able to make some kind of inference then about where the keys are in the world. From they've not told you exactly where the keys are. I mean, I'm not sure how else they could really communicate that. I mean, I guess there's a bunch of ways they could say to the left of the bookshelf or to the right of something else. And basically, when we're studying logic, we're studying, well, what are those valid forms of inference that we can make? So there's valid ones which guarantee the truth of the conclusion, and there's invalid ones that don't. So there's a few little bits of language that we're going to need to get started with this. One of which we've already talked about, which is natural language. So natural languages are those that come about naturally. So namely, English, French, Mandarin, those languages that we tend to talk in. Formal languages are those which are basically artificial. They're formalized systems. They have their rules and their grammar formalized. So there's two other bits of language that you might not be familiar with that we're going to introduce, though you may be familiar with these if you've taken a course in grammar or something. So syntax and semantics. So syntax is to do with the grammar of our language. That is, how do the words hang together? What are the legitimate ways of placing things together? So I forget what it is in the Jabberwocky, that poem where it says the lyre toad glibed and glibbled in the wabe or whatever. And that's clearly just meaningless. But if I said, John hat shoe, it's not really clear that I've said anything. I've said something. I mean, those words independently have meaning, but taken together, they're not telling you anything informative. And the reason is because it's just not valid syntax. It's not expressing any proposition in English to put things together like that. To the left of John, Mary is syntactically wrong. Whereas if I say John is to the left of Mary, then it's syntactically correct. So in logic, that's to do with, that is going to be what we talk about when we do our proof systems. So firstly, syntax is going to be important in terms of identifying, what is actually a legitimate sentence that we're allowed to have in propositional language. So if we have improperly formed sentences, then we're not going to be able to plug them into our inferential systems. But syntax is also going to be what we talk about when we talk about our proof systems, because our proof systems themselves are going to be purely mechanistic ways of basically assessing the validity of the combination of premises that we've got. And then semantics is to do with the meanings of words. So in natural language, it might be, it in quotation mark, cup, the letters CUP has 3 letters. That's to talk about the syntax, right? But the semantics of cup is that cup means cup. It means this sort of thing. Similarly, when it comes to our logical languages, when we talk about semantics, what we mean is tethering things to truth. So when we do syntax, we won't really talk about truth. We might, if we do, we'll talk about syntactic truth, but it doesn't mean this big T, truth like it is true. It's just a game of symbol manipulation when we're talking about syntax. Whereas when we're talking about semantics, we're getting into the realm of, what's actually true. So that's why I've kind of put next to syntax, proof systems, because I want people to kind of get that in their head early. And for semantics, I want to talk about models, because when we talk about semantics, what we're going to be doing is whatever our premises and conclusion are, we're going to be thinking about them in a model where certain things are true, certain things are false, and we're going to be evaluating those models. But we'll get onto that a little bit later. Then there's some other topics that we'll touch on. So meta logic, for example, is going to be doing proofs that are about the whole of our system. So the proofs in meta logic might be things that kind of tether together the syntax and the semantics, things that we'll probably talk about in the next lesson, to be honest, and not cover today. And proofs in meta logic can tell you other things, you know, about whether something is provable at all, for example, or whether every valid sentence in your language has an odd number of characters or something like that. You can do those sorts of things in meta logic. So those are logical proofs, as it were, about the logical system that you're doing. And then philosophy of logic, we might touch on a few topics in philosophy of logic, but philosophy of logic is basically the philosophy of all of this stuff. So what does our system actually tell us? You know, is it true of the world? Is this like the one true system? Is this the way that English language works? Is this the way that some other language works? What conclusions can we actually draw from, you know, the appearance that we have in our conscious experience of there's this thing called logic and this formal system we've created? What can we actually say about the world and the way it hangs together from that? So, as well, when it comes to logic, there's a lot of overlap between these different topics. So there's philosophical logic, and I suppose that there's even more ways you could pass this up, you know. So I've done a few episodes on the history of logic, and I intend to continue that series because I think that it leads into, if you want to understand why we do things certain ways in modern logical systems, understanding the history sort of gets you to see why something that might seem counterintuitive, how it's kind of come about, because these things have historical origins. So we have philosophical logic, right? And what we might be concerned with here is argumentation, such as, you know, if God does not exist, then there's no moral values or duties. There are moral values or duties, therefore God exists. So that's the kind of argument form that we're talking about there. In computer science, we might be interested in the logic of, for example, we want to write some program that captures some behavior on a website or something. And so we might want to say, you know, if button event, then do some behavior. Else don't, right? That's a really basic way of putting things. And then the same in mathematics, where we might want to, you know, do some proof about, well, suppose there is a highest prime number or something, and we're gonna, oh, what's another quite easy proof? The one that So basically, mathematical. I'm just thinking, what's the best thing to communicate that's not going to sort of assume any knowledge at this point. But basically, in mathematics, there's all sorts of theorems about numbers and the way that numbers work, which depend on certain axioms. So, like a successor relation, things like successor function, or relations between numbers, definitions like even numbers and things like that. And in mathematics, we want to use logic to prove things like that about the system. Now, there are areas where these things intersect. So, for example, we might have an intersection between, actually, potentially between all three when it comes to something like incompleteness, right? Because there are going to be philosophical implications about incompleteness, which is about the way that reality fundamentally is, or if we think numbers exist or mathematics actually exists, other than it being some language that we just talk about or something. There's going to be implications within mathematics, because you might be you might be in this world trying to prove, well, that one would actually be here. You might be in this world trying to prove, P equals NP, which is to do with solvability, or you might be in this world trying to prove Goldbach's conjecture. But that might be one of the things that Gödel's incompleteness theorem tells us just can't be proved, or something like that. So there's intersections between all of these, or for example, I might put here type theory. So if you're a programmer and you know about strongly typed, weakly typed languages and things like that, type theory also lies at the intersection between philosophy and computer science. So when it comes to propositional language, which we're going to be discussing today, I'm going to just give you a few kind of terms and definitions to sink into about natural language and formal language that are going to come up and you might not be familiar with when we talk about our propositional language, which is our first logical language we're introducing today. So our meta language is going to be a natural language framework. So we might say, for example, we might define something that we call and in our logical language. And our meta language is the language we're going to use to talk about our logical language. So, for example, we're going to introduce a symbol which is called and in our formal language. Now, you're probably not familiar with that already if you're just coming to this to learn logic for your first time. However, we're going to define that means and the way that we're going to do that is we can say, well, when we have two things like this, we can say that is true. And notice that we're using true, right, in the sense of natural language, and is the sense of natural language. If and only if, I mean, that's an abbreviation that you probably only come across as philosopher speak. But then we might say P is true, and look at that, we've captured our natural language, and Q is true. Now, there's a whiff of circularity about this way of defining things, and that is, that is kind of a bit weird, and we'll get into why that is when we talk about something like Tarski's schema of truth maybe later on. And there are things that sort of fall into this category of being more sort of philosophical implications that come about as a result of that, because just by introducing this one thing, it's not as if we've introduced anything significant that's kind of mind-blowing and going to change the way that you look at the world or reason about things. However, what we are trying to do is formalize everything and just make things a little bit more rigorous. And then what we can do is kind of explore that space that we've created and see, see what interesting things follow about that. So our object language then is going to be the formal language that we're stipulating, and our object language is the language we're talking about. So this thing, that is in the object language. And then we talk about that in the meta language here, right? Okay, so we talked a little bit about syntax and semantics. So a few things to remember so far is that syntax is going to be to do with our proof systems, and there are different proof systems. So if you've taken a long logic course before, read a logic book, are vaguely familiar with anything that you've tried to do in logic, you're going to know maybe one of these systems. So there's systems like natural deduction, for example. There's Fitch proof systems, Gentzen systems. There's Tableaux systems. And what we're going to do in this course is, I will eventually introduce the others, but at least initially, we're just going to introduce the Tableaux system. Then, when it comes to semantics, okay, we're talking about meaning or truth, particularly when it comes to logic, because our concern is truth aptness, right? So when it comes to semantics, we're going to talk about models, structures. So maybe you've come across things like truth tables before. And in a truth table, you have these rows, and each of these rows is going to be a different structure, right? Or a different model. So as you read across, each of these is going to be a different model with a different assignment of truth to each of those rows. Okay, so let's get into our first language then that we're introducing, which is propositional logic. Now, why propositional logic? So in philosophy, what do we mean by propositions? So proposition is basically the meaning of a sentence. So a sentence such as the cup is in my hand, or maybe I should hold the cup that actually has fluid in for me to drink. The cup is in my hand, right? Now, that I don't know enough. Maybe the snow is white, right? In French is la neige est blanche, right? Or is it masculine, feminine, or neutral in German? I always forget. But das Schnee ist weiß or whatever in German. Now there's a proposition. Well, this is a philosophically contentious point. This might not turn out to be true, but at least we're going to say initially that there's a proposition there which is being expressed in all three different languages. Now, the idea of propositional logic is that what we do is we kind of strip away the sentence-ness from the expression of propositions, and we just look at the truth valuable part. So what propositions are supposed to be philosophically are the truth about valuable part of a sentence. So it's nothing to do with the individual language it's expressed in or the grammar or anything like that, but it's the meaning of the sentence. And that can be true or false. It's false right now that the cup is in my hand, and it's true that the cup is in my hand when it is in my hand. So the idea of propositional logic is we're taking those straightforward propositions, we're looking at the kinds of inferences, which are relationships that there can be between those propositions, and figuring out which ones are true or false. So two other terms that I'm just going to quickly introduce. Firstly, logical atoms, right? The logical atoms are going to be the smallest truth valuable parts of our language. So these are just going to be sentence letters. So that's covered in our definition of the grammar of propositional language. The way we're talking about this is we've just got this big L, which signifies a language, and that P there is just to signify that this is our language propositional, whatever. So our logical atoms are defined here in this first part of our definition. So any sentence letter, A, B, C, D, E, that's going to express a logical atom, which is the smallest truth valuable part of our system. Okay, so then we have these well-formed formulas. Now, this is our meta language. This isn't a part of propositional logic, but the way that we're going to talk about well-formed formulas is by using these Greek symbols. So phi, psi, chi, omega. These are going to denote a well-formed formula. Now, a sentence letter is a well-formed formula, right? But there are also these longer well-formed formulas that we have here. And so the reason that we're going to refer to it's going to become useful when we're fleshing out the way that our language works to talk about well-formed formulas in the meta language. But a well-formed formula could just be a sentence letter, but it could be one of these longer ones with connectives. Okay, so we're defining here what a well-formed formula is, and well-formed formulas are the things that combine in our grammar of LP. So the next thing then that we're going to talk about is that if phi and psi are well-formed formulas, then so are, and then we've got each of these numbered definitions or denumerated definitions. So that little symbol there is not, so not phi. That symbol there is and or conjunction, so that's phi and psi. That symbol there is or, so we've got phi or psi. That symbol there is our material implication. There's a reason you might have seen that symbol as that elsewhere. We'll talk about this at some point in the course, but this symbol is generally used to translate natural language if then. But it's sort of a bit of a contentious question about how exactly you are supposed to translate that, and we'll get into those issues. The material implication is just a strictly defined logical form of, it's basically saying, okay, we're going to use this hook symbol because we're going to define it strictly in this way, and we're not concerned with that wider debate, basically. This one is going to be our biconditional. So our biconditional is if and only if, okay? And then we've stipulated here, nothing else is a well-formed formula of propositional language. Okay, so let's think about this then. Are these well-formed formulas? So our first one, just D, and feel free when there are these questions, if you want to pause the video and just think about it yourself, that might help the information to go in, and then you can resume playing and figure out if you got the answer right or not and test yourself that way. So just D on its own. Well, yes, D is just a sentence letter. So by clause 1, that is correct. It is a well-formed formula. 2, this one, P, then Q. Well, here we've got this. Maybe I'll use a different color. Let's go with green. So here we've got that. P then Q. So that is a well-formed formula. Okay, 3, A or B. Well, look, that's here, A or B. And so we've got that as a well-formed formula. What about 4, though? So what's the difference? Look at the difference between 3 and 4. Well, the difference is these brackets around the edge. And now this is where it becomes a bit unnatural, because in a natural language, you'll have learnt it since childhood to simply identify correct ways of manipulating symbols and incorrect ones. You know, if someone does something wrong, then you'll just be like, well, that's just incorrect. It's incorrect syntax. So if someone writes the sentence, you know, well, I'm going to write the sentence normally initially. So the first way that I'm going to write the sentence is, you know, the cat is on the mat, right? Like that. Now, the second way that I'm going to write this sentence, the cat is on the mat. And the third way that I'm going to write the sentence is like that. Okay, so this first sentence is completely syntactically valid and fine. But in primary school, you would have learned, if you'd written a sentence like this, then your teacher would have done this with the red pen. They would have gone, boom, capitalize, and they would have spelt it right. You know, full stop. Or if you're an American, they would have written period, which something about the red pen there is a little bit off. And if you'd written this, they would have just been like, if there were anything like my teachers, they would have been like that. Okay, so it's this, we have to sort of unlearn our familiarity with natural languages and the syntax of them when it comes to learning a logical language. And we need to now become consciously aware of the syntax and what's valid and what isn't. So actually, 4 is not a well-formed formula. And the reason is because it doesn't have the brackets around the outside. So you can see where the brackets are required in each of these definitions. Each of these two-place connectives, and we'll talk, I'll try and stop saying as well, if that's annoying you. When we talk about the number of parts that there are that are connected by a connective, we talk about its arity, or when we're talking about set theory, we'll talk about the arity of a relation or something. So alpha here has an arity of 1, whereas all the rest of them have an arity of 2 because they take 2 connectives. Okay, but you can see for each of these ones with 2 connectives, with 2 parts, that what the grammar tells us to do is to put brackets around the edge. And so 4 is not a well-formed formula. And basically the reason that we do this is it has to be rigorous this way. Otherwise, we start introducing sloppiness into our formal system that we're trying to create. So 5 here, we can see that that is a well-formed formula because taken all together, you know, A or B, that is a well-formed formula with the brackets around the edge. And then our negation symbol takes one well-formed formula, and it gets plugged in there. And now 6 is not a well-formed formula, okay? Because 6 doesn't have the brackets around the edge. But suppose we did have the brackets around the edge, then would that be a well-formed formula? Well, yes, it would be a well-formed formula, but look, you can see how having or not having the brackets sort of starts to introduce this ambiguity, because if we weren't strict about the application of our brackets, then we could get confused between 5 and 6, and 5 and 6 have different truth conditions. They mean different things. So are we trying to say not A or B, right? Or are we, or maybe, I mean, that's an and, so let's just ignore that and pretend it's not A or B. So are we trying to say not A or B, or are we trying to say not A or B? Because those are two different things that we might be trying to communicate, and that's why it's important not to be sloppy about our use of the brackets, even though it's very pedantic. And I might be sloppy about them, you know, in teaching propositional logic here. Okay, so let's introduce some more metalinguistic symbols that we'll use to talk about what's going on between our sequence in the language. So this little symbol here means syntactically entails. That's our syntactic entailment. So that will mean, if you see it, what you'll have is you'll have a series of premises and you'll have a conclusion. And if you see that symbol in between, it means that we've got some proof in our proof system between that goes from the premises to the conclusion and shows that the premises syntactically entail the conclusion. But that's a purely syntactic proof. It's purely about playing our game and applying the rules. This one with two horizontal lines through it means semantic entailment. So here, if you see this one, this means that there's some model in which all our premises are true. Okay, and that means that semantically our conclusion is true as well. This will become a little bit clearer as we talk through it. And this one here, this equals identity sign, what that means is that whatever's on this side is logically identical to whatever's on the other side. So what we've got over here has the exact same truth conditions as what we have over here. So this one will be true just when this one's true. This one will be false just when the other one's false. Okay, so what is truth? Let's talk about semantics a little bit, and that's a quote from Pontius Pilate. So truth is in a model or a structure. Okay, so this might become clearer in extensional semantics, which is something we'll touch on a little bit later, and that'll probably come in when we talk about quantified logics rather than propositional logics. So it's going to seem a little bit labored when we talk about truth in truth tables, as that being some kind of significant philosophical sense of truth. But it is significant in the sense that our truth in a truth table means that our proposition is true. Okay, but it's going to be harder to sort of model more complicated, or it's going to just not seem like that the definition of truth for propositional language is really what we mean by truth when we talk about truth in the world. But nevertheless, it is our definition of semantic truth in propositional language. So if we look over to this top right, what I've drawn in this box here, which is very lovely, is this U means this is our universe of discourse, right? And we've got two persons here, John and Sam. And John is orange, Sam is green. And then we've got this to the left of, which is going to be a relation between John and Sam. And we can see that that's true. We might say in natural language, John is left of Sam. And then we might create a formal language, which has things called, you know, like relations. And they take a certain arity of things. And we will do this when we get onto quantificational logic. And what we can do then is we can define an interpretive function, which is going to basically map variable names onto objects in our universe. And then we begin to see how we get a significant conception of truth, where what we're talking about in our formalized language actually does map onto some universe of discourse somehow. But when we stick to propositional logic, where things are going to be a little bit different from this, we're talking about truth in a structure. Okay, I mean, our universe of discourse over here is a structure. but it's slightly different to a propositional structure. So the notation for talking about truth in a structure is going to be this sort of thing. Now, it doesn't have to be S. We could have different structures. We could have a structure T. And indeed, before, when I talked about truth tables here, these are our structures. So we might have one which we call T. We might have one which we call R. It doesn't really matter what we use as long as it's clear in our communication. But these are our different structures as we go down the rows in a truth table. So when we have this notation around our formula, then we say it is true. We're using the equal sign, but we say is true with this big capital T, because we're talking about semantic truth, means that our formula is true in some structure S, which assigns truth to our formula. Now, again, everything seems nice and circular. And the point is that what we're doing is we're connecting together our natural language and our formal language. Okay, so we're going to define now our semantics for our propositional language. So firstly, our first clause, if A is a sentence letter of our propositional language, then here's that notation again, where we talk about structure, how our structure assigns S. Now, you might see this, and it's not incorrect. And we will do the same when we talk about quantificational logic again. But for example, in Graham Priest's book, An Introduction to Logic, he talks about the interpretive function like this. He'd say VA, or he might have a little subscript S under the function. He might talk about it like that. Now, it's the exact same thing. It's just that I think the interpretive function makes more sense when we are talking about this type of model here, because we can see how our function is directly mapping things to objects, and I think it's a bit more labored in the case of propositional logic. So I think I do prefer this notation here. But if you're reading a textbook or something, you might see this sort of thing, and it isn't wrong. So is true if and only if S assigns T to A. Okay, so that much is simple. Now, our next definition, our second one, if phi, or that's our stand-in for talking about a well-formed formula, is not B, then what we assign phi is true if and only if B is interpreted as false. So that's our definition of negation right there. That's not the right thing. That's our definition of negation. Then we have our definition of conjunction. So if phi is A and B, then phi is true. That's our whole formula is true if and only if A is true and B is true. So both parts have to be true. And notice here the appeal to the natural language and, right, to communicate that. That's the same in all of these, natural language or here. Natural language or here, natural language and or here. I mean, and or on their own are actually going to be what we'll call expressively adequate for our propositional language, but we'll come on to expressive adequacy a little bit later, and you'll see sort of why it is the case. But it is kind of circular because we're taking, our standpoint, our frame of reference, as it were, is our natural language. We can only describe a logical system or truth or any of these things from the standpoint of some language. And so we're formalizing things, trying to make them a bit more rigorous, and then we're able to explore, certain consequences that might apply to our actual conceptual structure that makes up our cognition, how we think about the world. But we can't sort of take off our natural language, as it were, and describe things from some non-linguistic point of view where we're trapped inside some language. So we have to, where our explanations come to an end in this case is our natural language, where we use and or and so forth, and even if and only if, right? And I guess if you just don't share a kind of, I'd have to say, well, you're just not a proper speaker of English or something. I don't know how I could communicate it to you if you didn't share. There's an assumption that you share an idea of what these mean in natural language, I suppose, in order to be able to communicate these semantic definitions. Okay, so our fourth clause, phi is this well-formed formula, A or B, then phi is true if and only if either our first disjunct is true or our second disjunct is true. So if either one of those is true, it doesn't matter if the other one's false, or they could both be true, then the whole thing comes out as true. Now our conditional. Okay, so our conditional is true if and only if the first part is false, that's our antecedent here, if that is false, or if the consequent is true. And we'll look at some truth tables, which might make these things more clear in a second. And then finally, phi, or biconditional, phi is a if and only if b. Then phi is true if and only if, firstly, the first part is true and the second part is true, or the first part is false and the second part is false. So you can see what's being got at there is that basically A and B have to have the same truth values. They have to both be true or they have to both be false. And we'll see that more clearly when we come into the truth tables in a moment. So modeling semantics using truth tables then, which is going to be our next point. So each of these, as we've said before, is going to be a structure, and we can read our structures across the horizontal rows of the table like that. So those are models. And this first truth table is a model of negation. So you can see that we have the negation symbol of P there. On the left, we have P. Now, when you're drawing a truth table, if this is your first time doing such a thing, then the way that you can calculate the number of rows that you're going to need to model the entire possibility space of combinations of truth is going to be the number of truth values in your logic. So in this case, we have bivalent logic, which means that we have the truth values T and F. So V equals 2 in this case, to the number of sentence letters that we're modeling. So in this case, we only have the one sentence letter, P, that we're modeling, and 2 to the 1 obviously equals 2. And so in this case, we're going to need 2 models in order to model what goes on, and we do have 2 models, so that's everything sort of mapped out. So now notice in terms of the semantics that each model tells us something different. So our first model here tells us that if P is true, then not P is false, and if P is false, then not P is true. That's our semantic definition, right, of what not P does. Okay, so conjunction, and notice in terms of writing this out again that we've got the same rule being applied. It's just a part of combinatorics. Maybe I'll do some other videos on combinatorics where we can cover why this is, why exactly mathematically this is the case. We're just choosing and combining a certain number of things. But so in this case, we've got 2 sentence letters, and we're still in our bivalent logic in this language, true or false, and 2 sentence letters. So it's 4, and so we need 4 models in order to model the entire possibility space here. And so we've got 4 models which cover everything. And the way that you sort of do this when it becomes when you're writing these out yourself is basically the first row, divide everything in 2. So go the first half of things, right, is going to be, and let's say we have 3, right? So if we have 3, it's going to be 2 cubed. So 2 cubed is 2, 4, 8. So take half that number and make them true, and half and make them false, right, is a quick way to do it. So true, 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 idiot, false, 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 false. And so we've just gone half and half in our first one. I mean, you could do this at 16, whatever, and then just half that again for the next row. So instead of 4 where we flip, we're going to flip it 2 now. So go true, true, false, false, true, true, false, false. And then, you know, for our third row, we half that again. So every 1 we flip true, false, true, false, true, false, true, false. And that will produce every combination that we need to look at in terms of modeling the entire probability space for our connectives over here. So in the case of and, which is our conjunction, which we defined here in this clause, clause 3. So in the case of and, we've got it's true, zoom out, it's true just in case A is true and B is true. So how does that look in our model? Well, that's this model here, where A is true and B is Q, or P and Q are both true. And so what we can do is assign it true in that case. However, it's false otherwise. So even though P is Q here, because Q is false, that makes this one false. P is false here. Even though Q is true, it becomes false again. And it's false in this case as well. So we can read the truth conditions off of these kinds of tables, off of truth tables, by basically going down this column here. And if you're, by the time you become comfortable with these truth tables and they're kind of in your mind, you won't need to do all this. You'll just draw it out like that instead of doing this. This is just for the sake of learning them. Okay, so we've got our disjunction here. So what we're going to do is true, true, false, false, true, false, true, false. What were our semantically defined truth conditions? Well, it's true if and only if A is true or B is true. So if either one is true, we can make it all true. So what about in this case? Well, both of them are true. So it comes out true. One of them is true, so it comes out true. One of them is true, so it comes out true. Both of them are false, so it comes out false. Hopefully that's kind of clear. Okay, material implication then. True, true, false, false. True, false, true, false. What was our semantic definition for this? So true, if and only if A is false or B is true. So what's that going to mean? A is false or Q is true. So we know that in both of these cases where Q is true, it's going to come out as true. And in these cases where in the cases where P is false, it's going to come out as true as well. So that's these two here, this one, which we've already set to true, and this one here, which we're setting to true now. But in this case, we don't meet our truth conditions, our semantically defined truth conditions are not met. And so this one is going to be a big fat false. Okay. So I talked about before translating between natural language and formal languages. Sorry, my brain farted for a second because I was thinking about having a drink of coffee. And this is a contentious one as to whether we ought to translate things these ways. So sometimes you will see this arrow used as the conditional, and that's generally when someone's a bit more confident in saying that this truth table is the correct natural language translation of if-then. I'm not as convinced of that, and maybe we'll talk about why at some point. But the reason that but something to bear in mind basically is that this definition of material implication, or the if-then, is basically the same as not P or Q. So remember the definition of or, which was that P or Q. So not P or Q then means is going to be true if either of these are true. So both P's are false here, but both P's are true here. So that's going to be true, true. And then Q, well, Q is true here, so it's going to be true, true, and it's false here, so that one comes out false. And now maybe I'll offer a tiny bit of commentary on translating into logic if-then statements. So if Oswald didn't shoot Kennedy, then somebody else did, right? That seems like a true proposition. You've got to look at the whole now. There's this sort of perspective shift when you're doing logic that you need to make between whole propositions and the components of propositions. So try not to think about that one at the level of each of its constituent components, but think about that one as the whole. And that seems like a true whole proposition, right? If Oswald didn't shoot Kennedy, then somebody else did, because we've got the fact that Kennedy was shot. So somebody shot Kennedy, right? So now think about the other one. If Oswald hadn't shot Kennedy, then somebody else would have. Okay, so it's not clear what the truth conditions for that exactly should be. It seems like one of those is true and the other isn't. Maybe I think I need to introduce the proof system a little bit later to really kind of paint the picture of exactly what might be wrong with translating between natural language and formal languages in this way, because there's an interesting intuitive case. There's an interesting intuitive case of circuits as well in natural language. So you can have a series circuit, and you basically have the proposition that you know, an in series circuit. Maybe I'll just add. I'm just learning how to use this iPad, by the way, so forgive me. But think of a series circuit with two switches. Right? Switch A and switch B. So you've got if A is closed and B is closed, then C lights up. And then in classical propositional logic, what we're basically going to be able to do is prove things from A and B, then C, logically, that aren't physically right about the properties of the circuit diagram. But we'll talk about that a bit more when we can actually do the proof to show that it's the right thing. So I'll bring that up again. And then our last one in propositional logic, which we had a semantic definition for, was this sixth clause. So phi A, if and only if B, then it's true if and only if A is true and B is true, or A is false and B is false. So that's easy enough. We come back to our truth table. How does that look? Well, we've got true, true, false, false, true, false, true, false. And keep in mind as well, if you've come to this from an electronics background or something else, that instead of true and false, you've probably just used, 1 and 0, and that's absolutely fine. That is the way that you're modeling things, right, in terms of truth and falsity in that case. So if both of them are true at the same time, well, we've got that there. Both of them aren't true and both of them aren't false at the same time here. So that's going to be false. Same in this case. And both of them are false here. So that's going to be true. So that's our truth conditional then for the biconditional. So let's use some truth tables to solve some things. And again, if you're watching along and you want to try this yourself, then pause it here and give it a go, and then just play and you can watch how I solve it. So here's how I'm going to go about it the long way, and then I'll show you a slightly shorter way using truth tables to prove these things. So firstly, what we're going to do is we're just going to draw a truth table, right? Having our two variables, P and Q, and then we've got P and Q. And look, I wasn't being rigorous, I was being sloppy, and I left out my thingies, my brackets. So, boop, boop, boop. True, true, false, false, true, false, true, false. So now all I need to do is think about our definition of and. I suppose what I should do in this case as well is, you don't really have to write that in, but I'm going to write that in there. True, true, false, false. And think about and. So it's true when both of them are true, false otherwise, false false, 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 false. Okay, so now what we're going to do, we're going to read across our models. And look, maybe I use a different color for that. Sort of pale greeny. Let's change this one to that. So that's all right. Okay. That's okay. But what have we got in? Then look at this one where it comes out as false. So it comes out as false here. Well, sorry, I didn't think about how to explain this before I started talking. So the best way to explain this is there's only one model in which P and Q is true, right? There's only this model, S1, because in all of these other models, P and Q comes out as false. And what we're concerned with is P and Q, right? So we don't care about these models because these aren't modeling the case where P and Q comes out as true. Only this model comes out with P and Q as true. So that model makes P true, and that's the only true model. There aren't any other possible combinations where P and Q come out as true. Is the one where P is true. Okay, how many examples do I have? Yeah, there's that one as well. So what I'll do then is we'll do this one in a similar way. Is P then Q, Q therefore P valid? Okay, so we're going to go same as before. P, Q, P then Q. Zoop, zoop. Like that. True, true, false, false, true, false, true, false. And now remember our truth table for this one. Basically, it's true in every case, except the case where the antecedent is true and the consequent doesn't follow. So that's the false case. And now what information do we know? What are we looking for? So the models that we care about are these ones. The ones where P and Q is true. So that's this, this, and this. We care about these models or these structures, right? And then we also care about the case where Q is true. So we care about, or is green on green going to be a bit vicious? So we care about this and this. So in this one, even though P then Q is true, that is false. And so we don't care about that one. And so what we do from here is, so now these are the structures that we care about. These two structures. And what was the conclusion of our argument was P. Sorry, my brain is going a bit weird. So the conclusion of our argument is P. So now let's look at what the value of P is in each of these structures. Well, it's true in one case and false in the other. So the question is this a valid argument? And the answer is no, because the truth of the premises, right, which is what we were looking for, the truth of these premises, P then Q and Q, which is what we were hunting for here. So we're hunting for true premises, right? And that's why we eliminated that there, because it's not true. So we eliminated our fourth structure. The truth of the premises does not guarantee the truth of the conclusion, because our conclusion in S1, right, makes P true, but our third structure, which is also a valid structure with true premises, makes false. And in a valid inference, we want to preserve truth. We move from true premises to true conclusions. Whereas in this case, the reason that this isn't a valid inference is because we would potentially be moving from true premises, potentially, I mean, we could still also be moving from true premises to a true conclusion, but the form of inference doesn't guarantee it. We could be moving from true premises to a false conclusion. And so it's not a valid form of reasoning. And this is actually a formal fallacy called affirming the consequent. Okay, so now we have a bigger one to do. So let's take a look at this. Remember that what we want to do is we have our number of possible logic values. Oh, just a comment that someone put saying, I'm watching through this. You might want to briefly mention what's being asserted by the propositions. P then Q asserts neither P nor Q. I don't know how long you've been watching, but I did cover that on when we did this truth table here. So we looked at that these two have the same truth conditions as well. Okay, so for this one then, and I did mention that, so the number of rows that we're going to need, the number of structures that we're going to need is going to be the number of truth values in our logic system, which is 2, true and false, by the number of, to the power of the number of variables that we have. So 2 to the 3, so 2, 4, 8, so we're going to need 8. Deliberately didn't do one with 4 because that would just be, you know, when you're doing truth tables at that level, it just becomes unwieldy. But so we're going to do 4 trues, 2, 3, 4, 1, 2, 3, 4, right? And there we go. True, true, false, false, true, true, false, false, and then true, false, true, false, true, false, true, false. Let's just have a little line to separate things. Okay, and I'll do that to separate our conclusion out as well. So now let's look at this. So what were our truth conditions for P then Q? Well, here, whenever the antecedent, this first part, is false, P then Q is going to be true. So these bottom 4 are all true. True, 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 true. And we can do the same for Q then R. Whenever the antecedent is false, well, it's not as easy. We'll do it a different way in a second. Well, let's do P then Q first. Okay, so P is true, Q is true. Well, that comes out as true. And look, this is just like a mini truth table, basically, of our if then that we had before. So P is true, Q is true, comes out as true. True, then false. Well, the implication, if the antecedent is true, the consequent can't be false. So that one does come out as false. Okay. And then what else do we have? Well, true, then false. That one comes out as false as well. Now let's look at Q then R. True, true. Well, that's going to be true. That's going to be false because it's true, then false. False, then true. False antecedent on both of these. So they're both true. True, then true. That's going to come out as true. True, then false. That's going to come out as false. False, then true, and false, then false. So both of these are true. And you can see why, because they have false antecedents. Okay, so what is R in each of these? Well, we've already got a column. I mean, our R column, it's kind of a little bit unnecessary because this is just going to be the same, right, either way. But I'm just going to do it for the sake of trying to make things clear if you're learning for the first time what's going on here. You know, because this obviously has to... This is our conclusion. So that column just goes true, false, true, false, true, false, true, false. And now what are we hunting for? Well, okay. The first of our premises, P then Q. When is P then Q true? Here and here. And in these 4. So we've eliminated 2 of our structures. When is Q then R true? Here, we've eliminated this one. These, well, we're only going to get that one out of that because that's when both are true. And here, and those are true as well. So now let's just read our models across as we sort of have done before. We have this one, this one, this one, and this one. Well, we have true here, true in the first one, true in the second one, true in the third one, but we have false here, falsehood. So, is this inference valid? Well, it might be on some interpretations of probability of what probability is, might be more likely. I mean, obviously, and being a bit crass talking about likelihood here, might be more probable that it would be truth preserving. You know, it seems 3 out of 4 times it is truth preserving, but it doesn't guarantee the inference. It doesn't guarantee that the conclusion follows, because there is a falsehood here. So we could be reasoning. Oh, and I did have actually what I did miss out here. Whoops, is that one as well. So we need to do. Let's go back. Well, let's just ignore it, because I did ignore it to start off with. Let's just ignore him. Sorry about that if you're watching this backwards, because I've already done the whole thing, and so I'd have to undo it all and start again to explain. So let's just pretend that that didn't exist. So this isn't a valid inference, okay? Because it could be the case that P then Q is true, Q then R is true, but R comes out as false. And that is the case in this model. So hopefully you can see that. Even though in S1, S2, S3, they all come out as true, S4 doesn't. Okay, and now a final example, which knowing a little bit about logic can help us with. So here's an interesting example called a Wasson. I think it's the name is pronounced Wasson selection task. And before you give it a go, I'm going to tell you that most graduates at Ivy League universities in the US, where I think these psychology studies have been done, didn't get this right. And this is actually used as evidence against the fact that the material conditional is our natural way of processing if-then statements, because most people do get this wrong. There seems to be some kind of cognitive bias that we have in trying to reason this way. But we have 4 cards. That's what each of these is. 1, 2, 3, 4. And each of them, each card, we are told, has a letter on one side and a number on the other side. Okay, so now we have a hypothesis. If a card has a vowel on one side, okay, vowels obviously being A, E, I, O, U, then it has an even number on the other. That's our hypothesis. Which 2 cards do we need to flip over in order to test this hypothesis, right? Well, let's think. What we're going to do first is similarly to how we've done things, and I do recommend that you pause the video and give that a go yourself, just to try it first. But now we're going to try it with our new logic from our truth tables, and we can get the question right. So we are going to use this color for E. So which of our models, let's write out these models again. S1, S2, S3, S4. In which of our models is E? Does E come out true? Oh, sorry. I just noticed it has a vowel on one side, is V. So it's when V comes out true, sorry. So that's going to be this one and this one. And maybe what I should have done before we started as well is, what are we looking for? What's our conclusion? Well, that's this column. So this one, and this one. Okay, so we have 2 structures in which we have a vowel on one side, 2 structures in which we don't. So for K, we're going to color that one in yellow. So K is these 2 structures, right? Now we're going to color in even number. So when do we have an even number? Well, here and here. Okay, and finally, I need a new color. Yep. When do we? Let's do U. When do we not have an even number? Here and here. Okay. So hopefully that model that helps you show the reason that I'm doing it this way is because if you recall, when we talked about semantics earlier, and I said that this sort of thing is going to make more sense when we do it, when we cover tethering together our syntax and our semantics in a quantified logic. But maybe you can see that the kind of conceptual space that we're modeling now, come on, work. I'm not good with my iPad yet. The kind of conceptual space that we're modeling when we look at this question with our truth table here. So we have 4 models, right? And one of those models is false. The rest of them, the hypothesis is true. Remember what the hypothesis was. If a card has a vowel on one side, then it has an even number on the other. So in these blue ones, we have our hypothesis is true. In this one, we have our hypothesis is false. So which card do we need to turn over in order to see? Well, the cards that we have, E, K, and 4, 7. Oh, what's going on in there? In the chat, just having a look. So the cards that we have, EK, 4, and 7. So we want to figure out if it's false. We have okay. So if we were, let's say we were to turn E over, okay. If we were to turn E over, and we know, by the way, I should have prefaced before I said any of this. We know that every card has a letter and a number on each side. So every card has a letter and a number. I should have said that. So you're not going to turn it over, and just have a color or have a picture of an elephant or something like that. Okay, so if we turn E over, it could be true or it could be false. Okay, if we turn K over, that's going to tell us nothing, because if we turn K over, it's true either way, so it's not going to be K. 4, okay, if we turn 4 over, it's going to be one of these two, this one or this one, and it comes out true either way. And if we turn 7 over, so 7 being this one or this one, well, in that case, it could potentially come out as false. So in order to test our hypothesis, we would need to turn over E and 7. And if we turned E over and we didn't have an even number on the other side, then we would have falsified our hypothesis. If we turned E over and we did have an even number on the other side, then our hypothesis would be true. Okay. And then if we turned 7 over and we did have a vowel on the other side, our hypothesis would be true. But if we turned E over and we didn't have a vowel on the other side, then our hypothesis would be false. So I hope that's kind of clarified how to think through that question. Okay, so what about proof systems then? I've not done a lot of talking about proof systems so far. So think of proof systems like a game of chess, where someone teaches you chess, like I recently did V, and you have your chessboard with, it's like, here's the board, each square represents a piece, and here's what you can do. So you can move these diagonally, or with the knights, right? You're going to say that is a horse. You can move these like this. You're going to say, I forget what the actual chess word is for these. You can move these like this. And this is sort of what our proof system is like, in that you're going to be taught some rules which you can basically apply to sequence, to strings of symbols in our language in order to figure out whether it's valid or not. Okay, so seeing one string of symbols enables you to apply a rule in a certain way. So when you see a proof system is going to tell you something that you can do with that, or with, that combination, or with that combination, where you can just you can basically apply rules over and over again, and if something happens, it's going to be syntactically valid. And if something doesn't happen, it's going to be syntactically invalid. Okay, so the proof system I'm going to teach initially is the Tableaux system. And I think that this is the best proof system, but there are other proof systems such as natural deduction, deNysschen systems, Fitch systems. Some of you might be familiar. The deNysschen system is like an axiomatic system. So where there are certain axioms which are tautologies, and you're just given those axioms, and then basically you can apply them with each other. When we do metalogical proofs, axiomatic systems are going to be better because they will enable us to more quickly and robustly sort of iterate across the entirety of our system. But for now, the Tableaux system makes far more sense as a proof system to be introduced first, and so I'm going to introduce it this way. Now, what we do with the Tableaux system is we take our sequent. A sequent is a name for our string of well-formed formulas, and assuming that it is grammatically correct, meaning that it satisfies all the rules of our language grammatically that we stipulated at the start in our first definition. Okay, so assuming it's grammatically correct, we are going to have certain rules in our Tableaux system which enable us to create a tree. Okay, and the creation of the tree is going to tell us whether it's proof theoretically valid or proof theoretically invalid. So valid is going to be when we end up with a tree where every branch on that tree is closed like this, and invalid is going to be when we end up with a tree where it has open branches like this. And in our trees, we start at the root node here. So that's our root node. And then at the root node, we have our entire sequence of formulas. We'll talk. Don't worry if this isn't making quite a lot of sense. This is just to give you the idea of the structure of the trees. So we have all of our formulas at the root node, and then we apply our rules over and over again in order to build out our tree. And we either reach a contradiction or we exhaust all our rules and we still have open branches. If we exhaust all our rules and we still have open branches, such as these, then we say it is proof theoretically invalid. Okay, so we have two well-formed formulas, phi and psi, and the sequent is phi syntactically entails, so that's what that symbol is if you remember it. Psi syntactically entails phi. So what our first move is to do in the game of building a Tableau is at our root node, we write down what's to the left of our entailment symbol. So that's this thing. And then we write down what's to the right of our entailment symbol. That's this thing, but we negate it. Okay, so that's our root node for the tree, this whole thing. Okay, so what's the next rule that we apply? Well, here are our Tableau rules. So if you remember, let's go back to, where were we? In our grammar, each of these are well-formed formulas. And what I've got here is a rule, a Tableau rule for each of the well-formed formulas in our grammar. Okay, so if on any branch you have well-formed formulas of the form A and not A, like this, then the branch closes because you've got a contradiction. So that's how you close a branch, like in the cases of these valid trees where each of them is closed. If you have formulas of the formulas singular, right? Formulas plural. Formulas of the form A and B, then you can introduce them one after the other on the branch like that. If you have formulas of the form A or B, then your branch goes like this. You split it and you go A on one side, B on the other. If you have A conditional B, or if A then B, then you split it like this, but you negate the A, the antecedent, and you keep B as it is. Now, that goes back, if you remember, where were we? To our conditional. Remember that our conditional is equivalent to not P or Q. So maybe you can see there why that rule is as it is. And then A, if and only if, or A biconditional on B splits into two. One branch is where both A and B are true. The other branch is where both A and B are negated. Okay. So now let's have a think about some other cases. So imagine that you had the negation applied over A and B. Well, by De Morgan's law, okay, not A and B is the same as not A or not B, and not A or B is the same as not A and not B. And what, if you can see, what sort of happened in these cases is we've taken our not and we've pushed it through the brackets, distributed it over each of the variables, and what's happened is our sign here has flipped from and to or to and. So in this case of not A and B, De Morgan's law means that that's just equivalent to not A or not B, where the not has been distributed over A and B, and our and has flipped to an or, okay, which is equivalent to that. So then we can just apply our rule for disjunction, and we end up with not A and not B on each of those branches. Similarly, in the case of not A or B, which is this one, not A or B, then our not gets distributed over the A and the B. So we've got not A and not B. And our or symbol gets flipped to an and symbol. And then we just apply our rule for and we end up with not A and not B on a branch. Okay, now let's think about in the case of this one down in the bottom left of the screen, not A, then B. Well, remember what I said before, that A then B is just the same as not A or B. So not A, in brackets, then B, okay, is going to be the same as not A or B. So again, in this case, we just apply our De Morgan's law. So the not gets distributed over both. Not A or not B. Not A is equivalent to A. It's just a double negation. That's the rule of double negation. Not A is just the same as A. So that becomes, and I did do something incorrect there as well, which the more astute amongst you, I didn't flip the sign. So we flipped the sign. So not A and B. So this is the same as this, not A or not B. So when we negate it, we've kept this is the same as this, and we've just appended onto the front the not. Okay, hopefully you see that. So then in the same way, we distribute the not over both of our variables, and we flip the or to an and. Okay, so by double negation, then this whole thing, not A, is just the same as A. So we end up with A and not B, which is just of the form of our conjunction over here. So it's essentially, I mean, this is a long-winded route, but we're essentially just applying our conjunction rule to then produce this A and not B, like that. And now maybe an intuitive way of thinking about when we have the negation over our biconditional, so that's our normal biconditional where we split them, and we have two different branches, one where both formula are true and one where both formula are false. Well, just think about maybe a semantic definition of what this means, okay? So not A if and only if B means that it's never the case that they both are the same. This is saying it's always the case that they both are the same. This is saying it's never the case that they both are the same. So how do we express that in our rules? Well, we have one branch which goes down where we have A and not B, which is one of the possible conditions. And we have another branch which we go down, which is not A and B, okay? And I could walk through maybe in a more syntactic way of expressing that, but I think the semantic way for that one is the best way to get your head around it. But there's a similar set of equivalencies as we did with De Morgan's and so forth to draw that out. Okay, so what are we going to do with this is our first question and then our second question on the right. So do you remember what we do at the root node? Our first rule in the game, if we go back, is to draw out what's to the left of our turnstile with the negation of what's to the right of the turnstile. So what's to the left of our turnstile here? We have P and P arrow Q. What's to the right of our turnstile? Q. So we negate it, not Q, just like that. Okay. So now what are we going to do? Well, let's just say we just have not Q there. So now let's move up to P arrow Q. Remember our rule for P arrow Q, which is this one here, not A, then B. And remember what I said about thinking of these as just rules in a game. So you don't have to think about what they mean. All you have to do is look at the symbol that you've got and then apply the rule. You know, just like you look at the knight and you're like, oh, I can move him around the board this way. Okay. It's just the same with the proof system. You don't have to think about meaning. You're just playing the game with the definitions. So with this definition, then we do this. So we're going to negate the first one, assert the second one. Well, look what's happened on this right side of the branch now. This one. We have got a contradiction. So we can apply our first rule for closing off the branch. But we can't do that on the other branch. Our other branch remains open. So what we're going to do on that branch is we're going to apply, we're going to go to our next premise, and we're going to look at what we can do with that. Well, we assert P, and now we have a contradiction there as well. So all the branches are closed, and we know that in the case where all our branches are closed, that is proof theoretically valid. So we can say that is valid. That is actually a proof of the argument form modus ponens, to give it its fancy Latin name. And now we've got this next one that we're going to do. So remember the rules of the game again. So we draw out our premises, not Q, P arrow Q. What's to the right of our entailment sign? We negate it. And remember, our definition of double negation is just going to allow us to eliminate that to P, basically. So those two nots just cancel out. And then we have our P, then Q. So similarly to before, that's going to become not P and Q. This side of the branch closes off. Then we have not Q And that closes off. All our branches are closed, nothing more we can do. And so this is valid as well. That is modus tollens. Now, these are argument forms that you can look out for, but hopefully now, if you've heard those argument forms applied before, you might have a kind of deeper understanding, proof theoretically, of why it is that they're valid. They're valid in a proof system. And you can also, if you're not satisfied, you could look at the truth tables for these. So let's just quickly do that. True, true, false, false, true, false, true, false, true, false, true, true, boom, boom. Okay, so in the first case, in the modus ponens case, what do we have? We have P then Q is true, so we have all of these, they're what we're concerned with. That's going to be the same in both, actually. And then we have that P is true, so we have this model. We have this model or this model, but okay, in that second model, S1, S2, S3, S4, in that second model, okay, P then Q is not true. So our premises aren't all true. So that model is not going to feature for us. So we only have this one model where both premises are true. That's where P then Q is true and P is true. And in that one model, which is our only option, Q is also true. So we can see why that's valid. And then when it comes to our second one, as we already said, that's the same. P then Q is true. And then our second premise, not Q, that we're concerned with. So we care about the cases where Q is false, which is this one and this one. Well, this one, again, P then Q is false in, so we're not concerned with that model. So the only model that we have where both P then Q is the case and where P then Q is the case and Q is not the case is one where P is not the case, which is this one here. And so you can see semantically as well as syntactically, here's your syntactic proof for both, why modus ponens is valid. Okay, I've got some more examples and then we'll call an end to this first lesson in propositional logic. So, two premises. Well, oh, sorry, we're doing it. I was about to draw out a truth table there. What I did forget to mention before was a quicker way using truth tables that you can actually hunt for a contradiction if something's going to be invalid. So, what you can do, so we only have P and Q here, and then we can write out our thingies, or our premises and conclusion. And what we're hunting for is any model in which the conclusion is false, right? But the premises can be true. So if we want to do that semantically, a quick way of doing that is to just assign falsehood. I can see there's going to be two possible ways of doing this, so that's why I'm doing it that way. So it's false just in case, those are our values, right? So what have we done there? Well, we've made P true when Q is false and P false when Q is true. So that makes the whole thing come out as false. And now we just basically go back and assign the values to those variables across the model. Okay, so it's just, true, false, 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 true, false, 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 true, false. So now we can look at the other premises in the argument, this one and this one. First, we're going to do Q then P. Well, the antecedent's false in both those cases, so they come out as true. And now we'll look at this one comes out as true. And that comes out as false. Okay, so you can see my brain's not working at this point. So you can see here that basically in this model, that's not right, is it? Oh, that's not even the right model. What an idiot I am. I made them both false. I should have made the way I should have done it is by making that true, and then what that would have done is that would have made it false. Okay, so then what that would have done to it, that would have also made, no, that would have still been true. But our problem would have been that in both of those cases, one of our premises would have been false. And so the problem is, semantically, that it would never have been the case that all our premises are true whilst our conclusion false. There would have been no models, okay, in which all our premises are true and our conclusion false, which is what we would have needed to show. We would have needed to produce a counterexample being a model where all our premises are true and our conclusion false, in order to say that it's invalid. Because we can't produce a counterexample, then we say that the inference is valid. So that's a quicker way to do it using Tableaux. To do it using truth tables. But now we're going to show the same thing using Tableaux. Yep. So how do we do that? Well, remember what we do at the root node. Like that. And then we negate our conclusion. Now, if you remember our rule, which is this rule here that we're looking at, this one. So we're going to go P and not Q, and on the other side, not P and Q, like that. So now we've done that one. Then we're going to go up and apply our next rule. So if you remember that one, we're going to go not Q, then P, and we go not Q, then P. And look at that. We've applied that rule now, and we have contradiction here. We have a contradiction here. We have a contradiction here. And we have a contradiction here. So our Tableau has now closed, and that means that it is syntactically valid. Okay, so now let's look at our second question. Again, we're going to take P, then Q, R, then S, not S, Q, and the negation of our conclusion. So not P. And then we just apply all the rules one by one. So I'm not going to bother. I'm just going to leave these on the branch. And then we go up and apply our next rule. So we split and we go not R, then S. We do have a contradiction on this side, but we still have one branch open. And then we're going to go not P, Q, and then we've done that one. We do have a contradiction here. So that branch closes. But importantly, this branch does not contain any contradictions. So we've exhausted our rule, okay? And that means that along this branch, all our premises are true. And the opposite of our conclusion is true, or our conclusion is false, right? And that's just on the assignment where R is false and not P is false. And so we say it's syntactically invalid. Maybe I'll write that in red. Invalid. And we could do the same thing. We could do the same thing with, let me just copy this. Semantically, by basically doing what I said before. So we're going to take our counter, or sorry, we're going to just, we write our conclusion along the top, but what we're looking for is an assignment that makes it false. Okay, so we've got P as false. So we can go along and fill in all our instances of P and make them false. What do we do next? Well, Q can be either true or false. That's why I introduced the new row. Not S can be either true or false. But if not S is true, that means S is false. Do you see? And if not S is false, that means S is true. Okay. And we only need, remember, even though I'm introducing more lines to the model, we only need one model in order to demonstrate that it's syntactically invalid. And what I should have done as well is that, because what we're trying to do is we're trying to prove it semantically. Okay, so do we have anything else that we can fill in? Well, we have our Qs, so we can fill in our Qs. False, false. We can see that in both of those cases, our first premise comes out as true. We can see we have our second premise, which can be, well, we only care about the case where it's true, so that rules out the second one. R then S, right? So we need R then S to be true as well. Well, basically, we just make R false. That's the wrong thing. Basically, we just make R false, which we're enabled to do, which then makes that true as well. And you can see now that it's all true and the conclusion is false. So this structure, which I'm going to call S1, so in S1 is the case that our first premise that's true. Our second premise is true. Our third premise is true. Okay. Our fourth premise is, why did I do that? Is true. But our conclusion is false. Therefore, it's semantically, is what I meant, invalid. Okay, so you can see how you can prove things either way. You can prove them syntactically using this proof system of Tableaux that we've introduced, and I'll introduce other proof systems in later episodes. Or you can prove them semantically using your truth tables like this. You can draw out the entire truth table and hunt for rows which make all the premises true and the conclusion false. Or you can try sort of make the conclusion false and hunt for a truth table, a row that's going to make the premises true that way. Okay. So we're going to stop after this slide, though. Well, I'll talk about what's on this slide first. So here's some more notation for you about our combinations of well-formed formulas. So we've talked a little bit about when I say some well-formed formula here on the left. syntactically entails some well-formed formula here on the right. And we've talked about in the case where some well-formed formula here on the left, semantically, okay, that's what we mean here, semantically entails some well-formed formula here on the right. Okay, but what about these different turnstiles? So these basically look the same, but they have a line through. It just basically means the opposite. So in that case, the well-formed formula here on the left does not entail the well-formed formula on the right. That just means all of everything on the left can be true. Or sorry, there's let's talk about things in terms of Tableaux, because we're talking about our syntactic entailment. So if we talk about things in terms of Tableaux, it means that there's basically some Tableau that we can create where with all of the terms that are in phi, with the negation of psi, and the branches that there are branches that don't close. That's all that means. Phi does not semantically entail psi, means that there is some model, some structure, a row in a truth table, in which all of our terms on the left, phi, are true, and our term on the right is false. Okay, now let's talk about tautologies, something which you may have heard before. In tautologies just means always comes out true. Okay, so our first way of writing, this is a syntactic tautology. So in this case, that just means it's always true. It's always a closed tableau. That it's always a closed tableau for a well-formed formula, and this just means true in all models. So every row. So sorry, let me repeat. Now I've kind of got my brain together. So the one on the left, that means that it's always going to be a closed tableau when we basically the way that we draw out that tableau. Let's think of a good one. So a good one is going to be here's one. We can do it like this. P, P, then P. Right. And so what we do, would be easier without that actually. But what we do then is we negate, P then P. And then remember from our rules of Tableau, we're going to do P, not P. We've got a contradiction, boom. And so you can see that that's always going to, that's just a logical truth. And we can show that syntactically, or we could show it in the truth table. If we were to do the truth table for P, P then P, true, false. So we have true, true, false, false. Both of those are true. So we can see that that's also a semantic tautology as well. Okay. But now there's also like other weird ways of writing that out, which means an equivalent thing. So when you see this symbol, but this time you can see that our phi symbol has shifted from the right to the left. Okay. And that just means that the truth table always closes. Similarly, in this case, it's moved from the right to the left, and that should be like that. They just mean the exact same things, okay? So these are all the same. These are all the same as well. So similarly, a contradiction is when it never follows. So, P and not P. We're going to do our Tableau. So we do not P and not P. What do we end up with? We end up with not P or P. Well, there's not P, there's P. Both branches are open, okay? It never follows because our counter conclusion, the Tableau for our counter conclusion never closes. So it never syntactically follows. It's always false. We could do the same for our truth tables, for our semantic definition. So we have P and not P, true, false. And then we have true, false, true, false. So the negation makes it false, true. Okay, so both of those come out false. And that means it's never the case semantically. Okay, it's always a contradiction, that P and not P. Similarly, you can shift that over to the other side without the line through this time, and it means the same thing. The reason that I decided to include this slide in the notebook is because it's my view that particularly this one, and this one and this one are a little bit weird and people don't often see them, but they are going to be useful when we come on to doing soundness and completeness proofs a bit later. So I wrote stop for today here. What we're going to talk about next time is conjunctive normal form, proof by induction on the length of a formula, expressive adequacy in a language, soundness and completeness theorems, and then we'll go into soundness and completeness. So thank you everyone for watching. I hope you found this useful. I think that most people who come in, if you have questions, like I see a question there that says, can you give the name for the symbols beside what they stand for? Turnstile is the name, but I did go over some of these things earlier in the slides. So in this slide, for example, so if you go back to the start of the video, and I will put timestamps in, you can go into that. What other logics will I talk about? After I do soundness and completeness for this language, I will talk about quantified logics first order quantified logics. Then I might talk about the distinction between first and second order quantified logics. Then what will I do? Do modal logics. So we'll do K, S4 and S5, or K, then S5, then S4, I suppose. Then we might talk about, some kind of weird things. So we might talk a little bit more about the conditional. Then I'll probably do some stuff talking a little bit more about epistemic logic, alethic logic. What do we think we're actually modeling? A little bit more about the philosophy of logic. Then we might come on to maybe completeness and incompleteness theorems of Gödel. Maybe I'll talk about after that halting problems, Entscheidungs problem, halting problems, and just sort of build out a little bit of a. Oh yeah, those would also be good things. Yes, compactness, model cardinalities, and stuff. That all Skolem, Lowenheim theories, all those things will come with the quantified when I come onto the quantified series. So I'm just basically, my plan, this is episode 1, is to just continue to build out a series from this point when I have the time and the motivation to do so, which I do today because I've been procrastinating. And in that series, just to build out, and I hope to touch on a bit of, hopefully there'll be bridges then between this series in logic and some other series I'm wanting to put together in linguistics. And I've started a short sort of philosophy of language series. I've got a short history of logic series. And hopefully that means that anyone with a relevant interest can just kind of build out from here and go into those things if they're interested. So hopefully it's been useful. If it has, then like the video, leave a comment if there's some sort of constructive feedback that you have for the series or a particular thing that you'd like to see. And I just hope it's been useful in some way. See you in a bit.